This is a third lecture on Section 7 of the typed outline for Stat401XV. It concerns a series of normal distribution or normal probability examples. It makes use of Table B3 in Vardaman and Job that we've already mentioned has a cumulative standard normal probability table. That table is set up roughly like this. There's two pages. The right-handed page down the left side has a leading digit and then a first digit after the decimal place for roughly values from 0 to about 3.5. Across the top are values for the second digit after the decimal place, 00 through 0.09. And then, for example, in this row and this column in the table is cap phi of 0.12. That is, there's a cumulative probability there for z less than or equal to 0.12. With that kind of background, you can ask yourself, well, then what should be the probability that a standard normal variable is less than 1? And I would find that in the 1.0 row under the 0.00 column. And a straight table lookup gets me that value is 0.8413, as I remember. And a straight table lookup gets me that value is 0.8413. If I ask myself, not what's the probability that z is less than 1, but what's the probability that a standard normal variable is between 0 and 1, then what I'm looking for is something pictorially that looks about like this. Here's my standard normal density with a mean 0 and a standard deviation of 1. And I'm looking for that kind of an area, that kind of an integral. And by symmetry, I know that this is 0.5, and so essentially what I've got to do is take cap phi at 1 and subtract cap phi at 0. This is 0.5, this is 0.8413, and I've got a value of 0.3413 for that probability. If I was to ask what's the probability that z is bigger than minus 2.13, then my picture is something like this. There's the number minus 2.13. I'm looking for that probability, and so this would be 1 minus that, and that's 1 minus cap phi at minus 2.31, and that's a table value, and so it's simply 1 minus 0.0014. That's 0.9886 when all is said and done. To change the setup a bit, I could ask the question, well, what about some probabilities if the mean is 1 and the standard deviation is 2? For example, what's the probability that x is between 1 and 2? Pictorially, I've got a normal distribution. Now it's centered at 1. The standard deviation is now 2. So that what I'm looking for is an area under a normal curve from 1 to 2. This would be 3 there. And I can see that, well, by making use of this little formula that says z values are values of a variable x with a mean mu and a standard deviation sigma that are x minus mu over sigma, I say to myself, well, this x equal to 2 has a z value of 2 minus 1 over 2, that is 0.5, and let's call that z number 1, and z number 2 has a z value, or the value 1 has a z number 2 of 1 minus 1 over 2, that is 0. And I find that what I'm able to do is to turn the probability problem with a mean of 1 and a standard deviation of 2 into a standard normal problem. So one with mean of 0 and a standard deviation of 1 if I use not 1 and 2, but rather 0.5 in place of 2 and 0 in place of 1. And what I'm looking for is the area under the standard normal curve from 0 to 0.5. And that's easily computed by taking 0.5 and plugging it into the standard normal CDF and subtracting phi of 0. This is 0.5 and this value is 0.6915, so that this difference is 0.1915. To take another mean and standard deviation, I could deal with a mean of 5 and a standard deviation of 0.31, and for example ask the question, what's the probability that such a variable is bigger than 4.81? Pictorially, what I'll be looking for is an area to the right of 4.81 when this curve is centered at 5 and has the standard deviation of 0.31. So I'm looking for that kind of an area. And in order to find that, what I can do is turn 4.81 into a z value by taking y minus mu over sigma. That is, taking 4.81, subtracting 5, and dividing by 0.31. Doing this computation, I have to be slightly careful here because that difference in the numerator is going to give me a negative value, and I can carefully do the arithmetic and find that this ratio is minus 0.61. And so what I want is 1 minus cap phi at minus 0.61, and that's 1 minus 0.2709, that's 0.7291. You've got to be careful when using this little conversion formula to do the numerator in the right order. Subtract the mean from the value of the variable and make sure that you carry the sign, because the sign tells you what's going on. It says that this picture is equivalent to a standard normal picture, one with mean 0 and standard deviation 1. If I go over to minus 0.61 and find this area. You've got to be careful to keep the sign right. Bottom line for these examples is that in normal probability problems, what you've got to work with amounts to a table for standard normal probabilities and this little standardization formula that says how to take values with a mean of mu and a standard deviation of sigma and turn them into values that I can look up using a standard normal table. That's all you've got. In some sense, this little formula tells you that there are really only 4 kinds of normal probability problems. I can give you 3 of the 4 entries of that little equation and essentially ask you to solve for the other one. And that's all the possibilities that there are. When I ask you to find a z value, essentially I'm turning it into I'm asking for a probability. Put it differently, if I give you a probability, that gives you a z value, and then I can ask for exactly one of those 3 entries on the right hand side. As an example of this, here is a little halfway realistic production example. You think of a filling scenario where you're trying to fill jars, and you can set some mean level by how an operator sets up a piece of filling equipment. But it's probably the case that the operator has not much control over how consistent the filling machine is. So you could think of a scenario here where one gets to choose a mean, is stuck with a standard deviation that's characteristic of the equipment that's being used. And here's the problem I'd like to set. The net weight of the label weight of the contents of the jar is 135 grams. So here is the weight, and a manufacturer or a food producer is promising 135 grams. The question is, how can one go about setting a mean fill level knowing that this distribution has a standard deviation of 1.6 so that the fraction of underfilled jars is not so big. The fraction of the underfilled jars is, say, 0.01. Now you can get that by moving this normal curve clear over here. In fact, you can make that value to the left of 135 infinitesimal, but that costs you something. This mean value that you get to set, every ounce that is above 135 is something that you've given away to a customer. If you promise 135 and you're actually giving 138, you're giving away on average 3 ounces or 3 grams per jar. If it's 140, you're giving away 5 grams per jar, and so on. So the idea is that I want to set mu as close to 135 as I can, but it has to be subject to having no more than 1% here, not having a tail that is too big on that distribution. So how could I set that up? Well, here's the way that I think. I think to myself that a standard normal distribution, if I draw a standard normal curve here, if I want 1% in the left tail, that's 0.01. And what I can do is I can look around in the body of the standard normal table and look for 0.01. And 0.01 corresponds to a z value. So I want this to be cap phi of z. That corresponds to a z value of minus 2.33. So what I can do is say that I want minus 2.33 to be equal to 135. That's the label weight of the jars, minus a mean over this 1.6. So what I've got is I've got an x, I've got a z that came from a probability, I've got a sigma, and I'm solving here for mu. And you can check out that solving that equation for mu says that I want mu to be 135 plus 2.33 times 1.6. That is, I've got to set the mean at 138.7 grams if I want no more than 1% of the jars to be underfilled, that is to have less than the label weight content. So essentially the difference between this and 135 is 3.7 grams, and on average I have to give away 3.7 grams per jar. If I don't like that scenario, basically what I've got to do is reduce that standard deviation by paying for a more precise filling machine.